Alright, this is another problem that involves Newton's law of motion. And in this problem, we have this block that is coming down an incline. And this incline is broken up into two sections. The first section has a elevation has an angle of 30 degrees, and the second section has an angle of 15 degrees. And we are told that the coefficient of kinetic friction at this first part of the incline is the same as the coefficient of kinetic friction at this second part of the incline. And we are asked to figure out what our acceleration is when our box reaches point B, which is right here. We're told that another piece of information we are told is that the acceleration that the box has on this portion right here is 3 meters per second squared. So let's figure out how to solve this problem. And the first thing we're going to do is, instead of using a XY system that we are accustomed to, we're not going to use this. We're going to actually we're going to turn our XY system so it changes, it makes our problem easier for us to solve. And we're going to change this. We're going to rotate it 30 degrees clockwise. And this lines up very nicely when we rotate it 30 degrees with the direction of motion that our box is going to have. So if we look at this box A and we draw a free body diagram, we have box A right here. Try to make it straight. And this becomes our Y direction, and this becomes our X direction. And we know that we've rotated it 30 degrees. And we also know that we are going to have some force that acts straight down, which is its mass. So the force of its mass is m times g, which is gravity, and gravity is going to be equal to 9.81 meters per second squared. And we're also going to have this normal force that acts perpendicular to the surface because it's on this inclined surface. And this normal force we're going to call N sub A. And another force we have to account for is this frictional force. As the box is going down the surface, it has some friction, and friction is pointing against the direction of motion. So our friction force is this direction, and our friction force is equal to mu k times N sub A. And we can equal this to a kinetic diagram. And our kinetic diagram is going to deal with our mass times acceleration. And our mass is, again, just going to be this m. And we're going to assume an acceleration along our positive x direction. And this is our acceleration of a. Now, we can sum our forces. And if we sum our forces in the x direction, which is positive this way, we get mass times acceleration in the x direction. We get minus mu k times na. And now we have a, if this is our y term, this is our x term. So we have a plus mg, and this becomes the sine of 30. So sine of this 30 degrees is equal to a mass m times this acceleration in the a direction, which we're given is 3. So it's mass times it's equal to 3m. I get this 3 because we're given acceleration of 3 here. But we can't solve this just yet. We have an unknown NA, and we have an unknown U sub k. So let's sum our forces in the y direction. And this is equal to the force times the mass times the acceleration in the y direction. For us, we just have a positive as up, so we have n sub a minus mg times the cosine of 30 is equal to 0. And why is this equal to 0? It's equal to 0 because there's no acceleration in the y direction. So from this we get our NA is equal to mass times gravity times the cosine of 30. Our next step, we can substitute this NA back into our original equation. So we have minus U sub k times mg cosine of 30 plus mg times a sine of 30 is equal to 3 times the mass. And if you notice, there's a mass in this equation, there's a mass in this part of the equation, there's a mass in this part of the equation, and there's a mass over here, so we can cancel them all out because each of our terms has a mass. So we have minus U sub k times the cosine of 30 plus g times the sine of 30 is equal to 3. And we can sub for this mu sub k, and mu sub k is going to be equal to 0.224. Well, that's good news because this mu sub k on the 30-degree incline is the same as the mu sub k in the 15-degree incline. And what we want to do now is we want to repeat this part, these steps we took, and we want to figure out the acceleration at b. And when we do this, we want to change our coordinate system. So instead of rotating at 30 degrees, we're only rotating at 15 degrees. And when we do that, we get a box here. We have our y coming up, and right here is only going to be 15 degrees. And we're going to have an x going in this direction. And this is equal to the same box in our kinetic direction, our kinetic diagram. And we're going to assume a mass times the acceleration in the x direction, and we're going to assume a positive acceleration. And when we put our same forces in, we have a mu k times na. We have a let's call this n sub b. We have a normal force on b, and we have a weight mass times gravity that acts at 15 degrees. Now we can perform all these same steps. So let's sum our forces in the y, and this is equal to 0 again because we know there's no acceleration in this y direction, which is up and down. So if we sum this, we have nb minus mg times the cosine of 15 is equal to 0. So nb is equal to mg times the cosine of 15. If we sum our forces in our x direction, so the sum of the forces in the x direction is going to equal a mass times an acceleration in this b direction, acceleration of b. So in the x direction, sum of the forces in the x direction, we have a minus mu k n times b plus an m times g times the sine of 15, and this is going to be equal to the mass, which is m, times the acceleration at b, which is what we don't know, which is ab. If we substitute this part of the equation in, or this term for mb in, and we substitute what we know for uk in, so we have 0.224 times mg times the cosine of 15 plus this mg times the sine of 15 equals m times the acceleration of b. Again, each of our terms has this m in it, so it just goes away, it cancels out, and we can evaluate this side of the equation for what AB is equal to. And when we do that, we get AB is equal to 0.416 meters per second squared.